Good morning, folks. How are you today? We are in lab number 4, which is on tempering of steels and impact testing. Here are our objectives. So, we are going to learn about the principle of IZOD and Charpy impact testing. And then we are going to conduct Charpy test on a variety of steels at room temperature and then a sub-zero or a very cold temperature. Through this, we want to study the effects of tempering and percent carbon in the steels on the material properties. A second part of the lab is we are going to measure Vickers hardness by measuring indents using Fiji, and we are going to compare the hardness values to those we get from the machine. And then, of course, as usual, we are going to critically evaluate the numerical results and make summary conclusions. And then, of course, at the end of this lab, you are going to submit a professional lab report in the specified format. Now, I have been a bit disappointed when I looked at many of your Lab 2 and Lab 3 reports, and I thought that I should look into it. And then I also went and looked at the videos that are posted on your companion lecture course 304 and 305. And I kind of got the idea that you didn't get the big picture of what this course is all about. So I do want to take some time in this lab to give you a big picture and tie everything together. So here is what I want to do. I want you to really appreciate the important role that materials testing and characterization plays in material science. And of course, material science is about relationship between structure, properties, processing, and performance of materials. So, especially for metallic materials, we are very interested in strengthening mechanisms. And all the strengthening mechanisms are tied to the motion of dislocations and their multiplication. So they are all tied to increasing the dislocation density and making motion of dislocation difficult. Then, of course, you have spent a lot of time learning about crystal structures. So I want to point out the common metallic crystal structures, which are these four: FCC, BCC, HCP, and BCT. We are going to talk about it a little more. And of course, throughout in the previous three labs, I have been emphasizing relationship between strength and ductility. And in this lab, I'm going to emphasize the relations between strength and toughness. We are going to talk about various measures of toughness: tensile toughness, fracture toughness, impact toughness. And then, of course, as I said, we have two parts in the lab. In the first part, we are going to do impact testing. And in the second part, we are going to do hardness testing. So again, big picture. This lab is about materials testing and characterization. Your course is about structure and properties of materials and how they relate to processing of materials. And then, of course, in longer term, we are interested in performance and cost, etc. So those are all tied here. So the key idea is these three things: structure, properties, and processing. So of course, by processing a material, we can change its structure and thereby change its properties. So if our goal is certain properties and we have a given material, then by processing it in different ways, we can get desired properties. So in metallic materials, the crystal defects are very important. Metallic materials are generally crystalline in nature. So we talk about four kinds of defects. We talk about point defects or zero-dimensional defects, like vacancy and solute atoms. We talk about one-dimensional defect. In fact, I just said dislocations essentially determine mechanical properties of metallic materials. So they play a very, very important role. And then, of course, we have two-dimensional defects like grain boundaries, and we have three-dimensional defects like second phase particles. So what we do is we manipulate these four kinds of defects to get desired mechanical properties in our metallic materials. So here is the role defects play in strengthening mechanisms. So the key thing in strengthening mechanism is we can make the material stronger if we can create obstacles to dislocation motion. If we can make moving dislocations more and more difficult, that means it requires more and more stress, then we make the material stronger. As the dislocations move, they multiply. So in the process of their motion, they also become stronger. And this is the key idea behind strain hardening. So when we cause plastic deformation, we cold work a material. Okay, so how can we make dislocation motion difficult? We can place zero-dimensional defects as obstacles to dislocation motion. So this is called solid solution strengthening. So this is like when we dissolve carbon in iron. Iron usually is a very soft material. But when we put in tiny amounts of carbon, this iron becomes quite strong and we call it steel. Of course, we can put one-dimensional defects as obstacles to dislocation motion, and this is what we do during cold working. We're going to talk a little more about it later on. Then, of course, we have two-dimensional defect like grain size. So we call it grain size strengthening, and we do so by reducing the grain size. By reducing grain size, we increase the number of grain boundaries, or we increase the grain boundary area per unit volume of the material. And then, of course, we can place three-dimensional defects like second phase particles as obstacles to dislocation motion. And one example you saw was precipitation hardening when we were looking at the two different kind of aluminum alloys. So here are four common metal crystal structures. Face-centered cubic, like copper. Copper is FCC. Face-centered materials are usually soft, they are ductile, and they don't show a brittle to ductile transition temperature. We are going to talk about that a little later on, but I'm giving you an overview. Body-centered cubic materials like iron. These materials have kind of medium strength and medium ductility. And they do indeed show ductile to brittle transition temperature. Hexagonal close pack materials. Hexagonal close pack materials are brittle. Not only that they are brittle, they also have kind of low strength. And then, so one example is like zinc. Then we have body-centered tetragonal material. Now, of course, they can have variety of properties, but in general, body-centered tetragonal materials are very strong and very brittle. An example is martensite. And again, we are going to talk about martensite little later. So here is the relationship among mechanical properties. So when we did tensile testing, we saw that strength and ductility were inversely proportional. So if we did something to increase strength, we decreased ductility. Then we did hardness testing, where we measured indentation hardness, and we found that hardness was proportional to strength, yield strength specifically. In this lab, we are going to do impact testing. So we are going to measure something called impact toughness, and we are going to find out that impact toughness is inversely proportional to strength and hardness. So if we do something to increase the toughness, we are going to decrease strength and hardness. So here is what we did. We did a tensile testing. We got this tensile testing curve. And as I explained in an earlier lab, there were four critical properties that we measured. Elastic modulus, which was the slope of this initial elastic portion of the curve, which ended at yield strength. And then we had uniform plastic deformation, which ends at tensile strength. And then the material fails and we have ductility. So we have four key material properties: elastic modulus, yield strength, tensile strength, and ductility. Now, since we are going to talk about toughness, imagine another property which would be area under this curve. So roughly on the schematic shape, we can kind of think this as a trapezoid. So if we think this as a trapezoid, it has a width of ductility, this epsilon f. The average height of the trapezoid would be sigma y plus sigma t over 2. So that would be our trapezoidal area, and this is called tensile toughness, the area under the curve. And here is what we did. So it appeared that there was some confusion, as I gathered from the lab report. So what did we have? We had two steel samples and two aluminum samples. So for my aluminum sample, I had a red and a green sample, right? So what we did, we took this red sample, put it in the tensile testing machine, and we broke it in two pieces. We took this green sample and broke it in two pieces. Then for your lab, I had given you a blue steel sample, which we broke in two pieces. And a yellow steel sample, which we broke in two pieces, right? So here were our samples. So aluminum samples, this red sample was solution annealed. So it has a single phase. So it is in its softest condition. So you can see it has low strength, but very large ductility. Let's compare it to the green specimen. So in the green specimen, we gave it a heat treatment. We created aluminum copper precipitate. So they were second phase particles. So we dispersion strengthened it, or precipitation hardened this red sample to this green sample. So we saw green sample had higher strength and lower ductility, right? So by increasing the strength by dispersion hardening, we decrease the ductility. Okay. Then you did the steel samples. What is the difference between steel samples? The blue sample was just skin rolled. That means only the surface was cold work or plastically deformed. The yellow sample was quarter hard. So its thickness was reduced so that we achieved about quarter of the hardness that we could achieve. So the highest amount of rolling would give it fully hard condition. And then I analyzed the results. First of all, I said, look, elastic modulus doesn't change when we put in a little bit of carbon in iron or we put in a little bit of copper in aluminum. However, the yield strength changes dramatically when we put in those small amount of solutes, carbon in iron and copper in aluminum. And then, of course, I just spoke to you about the mechanical working that we gave to steel and the heat treatment we gave to aluminum. We did precipitation hardening, heat treatment, and we did this surface rolling to quarter hard, cold rolling, which is mechanical treatment to make blue steel or yellow steel harder than blue. We gave precipitation treatment to make green harder than red. Okay, so let's talk about toughness. Toughness is the energy required to fracture a specimen. So this tensile toughness, we just spoke about area under the stress strain curve. We made this tensile test we did when there was no notch present. And we did it at a very low strain rate. In fact, we called it static tension testing. So this area under the curve is a measure of tensile toughness. It's a qualitative measure. Of course, it's a fairly simple and inexpensive test. The key measure when we really want to measure toughness of materials is called fracture toughness. So there is this stress intensity factor which has a critical value for a given material. So I want you to read about it, see your textbook. I think your professor is going to cover it in your lecture course. But this fracture toughness is measured when our specimen has a very sharp notch or crack. And then we deform the specimen at a very low strain rate and we measure how this crack grows. So this is a truly quantitative measure. However, this fracture toughness test is very complex and expensive. Then, of course, last is impact toughness, which is energy absorbed during impact. Here, our specimen has a notch and the sample is deformed at a very high strain rate because we load it under impact condition, instant condition. And again, even though we do get a number, just like we got a number here, area under the curve is a number, but it is not a number we could compare quantitatively. So same way here, we'll get a number, but it'll be just a qualitative measure. We can say something is more tough than other. However, it is a very simple and inexpensive test. So again, remember, tensile toughness was area under the curve, large area under the curve. Typically, when the material is ductile, we say we have a very tough material. When we have no plastic deformation or relatively little plastic deformation, you can see the area under the curve, even if the strength is high, is very small relatively. So we call such a material brittle material. It has little toughness. So here in Lab 4, again, let's look at the objectives. We are going to learn about IZOD and Charpy impact testing. Then we are going to conduct Charpy test on various steels at room temperature and at a very cold temperature, sub-zero temperature. We are going to study the effects of tempering tempering of steels and percentage carbon in steel, on material properties such as impact toughness, hardness. And then in the second part of the lab, we are going to measure Vickers hardness using Fiji, and we are going to compare hardness values. And then, of course, we are going to evaluate our results, make summary conclusions, and for your lab, you are going to submit a professional lab report. Okay, so let's see, why do we do impact testing? So impact testing is very important in industry. We do it to measure impact toughness. We do it to study ductile to brittle transition. Often impact testing is only used for qualitative comparison, no quantitative comparison of similar materials, typically materials that have been given some thermal treatment or mechanical treatment or thermomechanical treatment. It's very simple, quick, and inexpensive testing, as you will see. And in industry, often it is used to monitor heat treatment for quality control purposes. So samples are usually small like this. And imagine, suppose you have a big forging that is being given a heat treatment, or a particular big die or a bar or a shaft being given a heat treatment. So what they may do is they may put in several of these samples along with the part being given the heat treatment. And then when the heat treatment is complete, we just test this particular piece, which is a destructive piece. It's a destructive testing, and we can figure out if it got proper heat treatment or not. The applicable ASTM method is E23. Please download it from the library and study it. We are going to talk about two kinds of testing, IZOT testing and Charpy testing. Both are used to measure impact toughness. This is much more common in Europe and Canada. Charpy is much more common in US. So instead of looking at just this piece, you will see that in the video I'm going to show soon, basically our instrument consists of a swinging pendulum. The pendulum impacts upon the specimen, breaks it, and we measure how much energy is absorbed. There are two ways in which we can configure our specimen. One is we can hold the sample vertically. This is called an IZOT test. In this case, notice that the notch should be towards the specimen. Towards the notch should be towards the pendulum. So as the pendulum swings, it's going to break the piece in two. Here in Charpy, we put the sample in this horizontal position, so it is resting against these two supports. And here the notch is facing away from the swinging pendulum. So as the pendulum swings, it breaks the piece again in two. So let's watch this video. Good afternoon, folks. This is our impact tester. It is made by Satex Systems. It is model SI1C3. There are different parts to this equipment. One, we have this lever arrangement which controls the swinging of the arm. Second part is our dial, where we are going to make our readings of the impact toughness. And third part is this swinging arm. So let's start with the top. This lever has three positions: a brake position, a release position, and a latched position. So when we put it in latched position, we can raise the arm at two angles. One is at 45 degrees and one would be at 135 degrees to the vertical. So when it is at 135 degrees to the vertical, we can store a lot of energy, up to 300 foot-pounds or 4,000 joules or so, 400 joules or so. And this scale is used for very ductile materials. because we need a lot of energy to break those ductile materials. The upper scale is limited to 125 foot-pounds. This is when we latch our arm to 45 degrees to vertical. So this 125 pound scale, we use it for brittle to reasonably ductile materials. This is the scale that we are going to use today. And then of course we have the swinging arm, which as I said, we can latch it at 45 degrees or at 135 degrees. So as I said, we have two kinds of tests, IZOD and CHARPy. They are done in the same machine. Now in the video you saw that our hammer swings from right to left. Here in this diagram, it is swinging from left to right. The only, therefore our directions and notch directions and swing directions would be just the opposite. We have two kinds of samples, IZOD and CHARPy. IZOD is slightly longer, so you can see it has the same cross-sectional area, except that 55 millimeter long, CHARPy has the notch in the center. The IZOD is 20 millimeter longer because it has to be held vertically like this, like I am holding it in my hands in our machine. So now when the hammer comes, it is going to swing and hit it like this, break it in two pieces. So this is what the geometry shows. Now in CHARPy, what we do is we have the notch facing away from the striker, and it is just held in place, and the striker then comes, hits it right in the center, as you will see in the video a little later on. So notice if there was no sample here, what would happen? If we held the striker at a certain height, it'll swing and go to the other side, reach the same height. No energy would be absorbed. However, if there is a sample in there, when the striker hits the sample, some energy would be absorbed in breaking it. And that is what we want to know, and that is what is called impact toughness. So let's see how our machine is set up next. Okay folks, so we are going to break one of our CHARPy samples. This sample has a notch at the center. We are going to show you in a enlarged scale in a different figure. But here is our procedure. We put our lever into latch position. We are going to raise our arm about 45 degrees and it locks up. We are going to set our pointer to max position. This is all calibrated. So we have stored some energy. And now, right now, we don't have any sample. So if we release the arm, no energy should be absorbed. So our pointer should point to 0. So I'm going to release the arm. And you can see that the needle reads 0. So we are going to break the swinging of this pendulum, and that is our reading. Okay, so I have 5 steel samples for today's lab that we are going to test. I'm going to only show you how to test on one sample, just to keep this video short. Here it is. Okay, so we are ready to break our sample now. So we will go through the same steps again. First, I'm going to latch the lever. I am going to raise the arm latch it. I am going to put the needle to its maximum position. And now I have my sample. What I want to do is, it has a notch in the center and I want to break it in two pieces like this. So I want to apply a force on the opposite end of the notch. So what I'm going to do is, I'm going to put the notch facing that way into the machine. And the striker is shaped just like my finger. So the striker is going to come, strike at the back of that notch, break the sample in two. So let's go, let's see. So I'm going to now break it. I'm going to make a reading. This reading comes out to be 18 foot-pounds. My sample has broken. And I have collected my sample. So the testing we just did was when specimen was at room temperature. So we got the room temperature impact toughness. It turns out that some ductile materials, which are ductile in tension testing, fail in a brittle manner. So there is a ductile to brittle transition. Now this transition can happen because deformation is at a relatively low temperature. Or maybe the deformation is at a high strain rate. A third possibility is that there is a triaxial stress state introduced by presence of notch or crack. So often we are interested in effect of temperature, testing temperature, or temperature of service, what effect it has on this impact toughness. So here is a typical graph. Let's say this was our testing temperature. That means the temperature of the specimen. And this was the impact strength. So for a material that shows this transition, what we might see is at relatively high temperature, the material has high impact strength or impact toughness. So it is ductile. Then as we start decreasing the temperature, in a certain temperature range, there is a drastic reduction in impact toughness, and the material therefore appears brittle. So there is a ductile to brittle transition, and usually this middle temperature or the inflection point is what we refer to as a ductile to brittle transition temperature. So here is some characteristic curves. So typically we know that steels at normal temperatures, room temperatures or so, have fair amount of impact toughness. And they show a ductile to brittle transition at low temperatures, they suddenly appear very brittle. Now, there are materials which are low strength. Notice we are not plotting strength here, so this curve is shown as higher. These low strength materials are very ductile. Since they are very ductile, they also have high impact toughness. And it appears FCC and HCP materials have high impact toughness, and therefore they may show a transition, but they don't. Only these BCC materials show this transition. Now, in this particular case, imagine they may have a ductile to brittle transition, but the transition temperatures may be far too low, much lower than even the service temperature. So therefore, we may not be interested in that transition. Now, if we have high strength materials, say we have hardened the steel. Now, when we harden the steel, we know that we reduce ductility or we reduce its toughness. So as it is, they are low toughness. So it doesn't matter what the surface temperature is, they are going to remain pretty much low toughness. If they were brittle at high temperatures, they remain brittle at low temperatures. So we don't see any transition. So here is, for example, FCC versus BCC steels. So here, stainless steel, which has a FCC structure, you can see it doesn't show any transition from minus 200 to 400 degrees Fahrenheit. Whereas plain carbon steel, which has a BCC structure, especially this low carbon steel, shows this transition temperature. So at 200 degrees or so above, it is very ductile, 300 degrees or above ductile, and then it becomes brittle below at about 100 degrees F or so. So here is, for example, what the surfaces look like when the sample is fractured. So here is an example from the textbook, A36 steel. These are the testing temperatures in degrees C. Notice we are moving degrees Fahrenheit, degrees C, depending on the source. And you can see at very low temperatures, the surface looks very shiny, okay? Very, very smooth. So this is brittle failure. As we move to the right, you can see the shapes change quite a bit. So this is your Poisson's effect you are seeing. More and more plastic deformation as we go from left to right, and the material is becoming more and more tough and ductile. And you will see more plastic deformation. So here is the effect of carbon content. So again, here on x-axis is temperature of testing, y-axis is impact energy absorbed. So you can see, first of all of these plain carbon steel samples are showing transitions. So they are going from tough to brittle, okay? And as we change the amount of carbon content, for instance, first of all, you see that the room temperature toughness goes down. So let's write this up. As percentage carbon increases, room temperature toughness is going down. So that's our these values. Next thing you are seeing is that the ductile to brittle transition temperature is going from low to high also. So as percentage carbon increases, ductile to brittle transition temperature is increasing. And notice at low temperature, the impact energy absorbed is all about the same. They are all about zero. They are all about brittle. Now, you may think that this was known for a long time, but this ductile to brittle transition was only scientifically understood in 1940s. They started observing number of failures at low temperature. The most spectacular were these Liberty ships during World War II. And you might want to read further, it is in your textbook. And you can see there were number of photographs as they went out to sea. They experienced low temperature and they just split in half. Now we are going to measure impact toughness today, and we are going to measure hardness. Now for materials that are exhibiting ductile to brittle transition, of course, we are going to measure impact toughness at some room temperature and at a relatively very low temperature to see if there is this transition or not. So what we are going to see is, of course, impact toughness will likely correlate inversely with hardness, because we know if we increase the strength, typically ductility goes down, and we expect toughness is likely to go down. And we know strength correlates with hardness. So when hardness increases, strength increases, so toughness should decrease. So our hardness to toughness correlation would be this. Now it turns out that hardness does not change very much at low temperatures. So of course, if the material becomes brittle, we will see no correlation with hardness because it'll show same zero or near zero impact toughness. Okay, before we go on to impact toughness, let's take a look at again at our tensile properties from Lab 2. So instead of using our experimental values, I'm going to use published values. Okay, much more reliable. And remember, I said tensile toughness was roughly this trapezoidal area, and this was our formula. So here are the results. I was just jotting down to calculate them. I've just copied them. So you can see I have blue and yellow steel. This is skin rolled. This is quarter hard. So we have strengthened it as we go from left to right. This is aluminum copper alloy, red green, solution annealed. And this is precipitation hardened. So of course, due to strengthening, we see increase in yield strength, increase in tensile strength, decrease in ductility. Same here, for upon strengthening, increase in yield strength, increase in tensile strength, decrease in ductility. Now, if I use this formula, I find out that the tensile toughness, putting these three values in this formula, is 15.6 K here. So upon strengthening, the material becomes less tough. Here, on the other hand, in aluminum, notice upon strengthening, strength increased quite a bit, but the tensile toughness also increased. So in this particular process, not only we increase the strength, we increase the toughness also. So when I said strength increases, ductility decreases, usually the toughness decreases, but not necessarily so. It depends on the mechanism by which we have increased the strength. Okay, again, I want to repeat. These are our objectives. So let's look at our specimens. So 5 specimens. I have a white, a blue, and a white specimen. So our white specimen is 0.18% carbon steel. Blue is 0.45% carbon steel. So here we want to see what is the effect of percent carbon. Then I have 3 more samples of 4140 steel. So remember, last 2 digits means 0.40% carbon. First 2 digits tell us that it is a low alloy steel. It contains 1% manganese and 1% chromium. So all of these samples were first quench hardened. So what do we mean by that? So I have these 3, red, yellow, and green. So quench hardened. So we took this steel, heated it to high temperature so that it becomes what something called austenite. We are going to talk about this austenite in the next lab in great detail. You are probably going to cover it in your lectures somewhere about this week, next week. But essentially, when we take the steel, we heat it up, we form austenite, and we quench it. That means we cool it very, very fast, like dropping it in cold water, and it forms martensite. So this has a FCC structure, soft. This has a body-centered tetragonal structure. This is very hard. Since it is very hard, it is very brittle, very low toughness. So it does not have very much use directly for products. So what we do is we temper it. That means we reheat it. So we take this martensite and we reheat it. So what happens is this martensite becomes tempered martensite. Again, we are going to talk about, you're going to learn about it in your course. But basically, tempered martensite, some carbides precipitate out. So what happens is this material, which was very hard, becomes softer. And of course, the toughness increases. So by tempering it at different temperatures, we can get different combinations of hardness and toughness. So we have tempered it at low temperature, tempering temperature, 400 degrees Fahrenheit. Its hardness is about 47. Higher temperature, hardness is lower. Very high tempering temperature, you can see it has the lowest hardness. So what we are going to do is we are going to measure its impact toughness. So now in my demo, I'm only going to use data from one set of specimens. So one set of 5 specimens. Then what I'm going to do is for your assignment, I'm going to give you 3 sets of data that you are going to average. And the reason is typically in impact testing, there is such a scatter in our measured values that we really ought to be testing 5 or more samples. So we have at least 3 sets. You are going to average them, and then you're going to do the processing just like I'm going to show you in the next few slides. So again, remember, effect of carbon content. As we increase the amount of carbon, we expect toughness to decrease. So here is effect of tempering temperature. So temperature on x-axis. On y-axis, we have yield strength and hardness. And on secondary axis, we have ductility. So notice, as we increase the tempering temperature, the strength drops, tensile strength, yield strength drops, hardness drops. They all correlate well with each other. And notice the 2 measures of ductility increase. So by tempering, we are paying the price in hardness and strength, but gaining it in ductility and toughness. Okay, folks, so please create an Excel sheet named Impact to follow along. I have posted this on my courses, again, PDF format. I know a few of you have complained that I should give you the Excel spreadsheet directly. And I have tried to explain that I want you to appreciate what it takes to create a functional, nice looking spreadsheet. In any case, if you were taking an in-person lab, you would have had to transcribe all these values from your handwritten data into the spreadsheet. So I hope you take the time to build the spreadsheet and enter this data. So let me fire up my spreadsheet. So as usual, we have our title, we have our method inputs. These tests were performed in spring semester last year by Professor Humphrey. This was the hardware used uh, and ASTM standards. And I already told you about the different steels. So we have 5 steel samples. First 3 steel samples are 4140, tempered at these 3 different temperatures. Next 2 different carbon steels. These are the carbon contents. And then last spring we measured tensile toughness at not tensile toughness, impact toughness at room temperature using our impact tester. Then we also measured toughness at low temperature. We don't quite know what the temperature is, but I guess the temperature is around minus 30 degrees or so, 30 degrees C. And of course, we did 4 hardness measurements on the specimen before we did the impact testing. So these are 4. When we have a lot of data and when we are transcribing it, especially when we are transcribing it from paper onto, say, a spreadsheet, or we are copying it from one form to the other, like you would be doing, you'll be copying all this data. So what you might like to do is you might like to just check whether you have not made any transcription error. And one very easy and quick way is to do a checksum. So what you can do is you can go from this cell C15 all the way to G20, total it up, and make sure that in both formats the sum matches. All right, so our processing is very simple. We are just going to take average of these hardness values, 4 hardness values. And then we are going to take this formula, copy, and we are going to paste formula only to the next 4 cells. That's all the processing we are going to do. Now we need to create some plots. We are going to create 2 plots. We want to plot against this tempering temperature our room temperature toughness, our low temperature toughness, and our Rockwell C hardness. So I'm going to insert an XY plot with dot and straight lines. Now I don't want tempering temperature on the y-axis. I want it on an x-axis. So I want to switch row column. So here is on my x-axis, I have my tempering temperature. So as always, move the chart to a new sheet. Let's call it plot number 1. Okay, the first thing we are going to do is format the axes. So our temperatures go 400 to 1200 and spacing of 400. Okay. All right. So these two, blue and red, are our impact toughness. So they have different units. This is hardness, different units. So let's move this to secondary axes. Okay, let's format these axes also. This goes from 0 to 90. It looks about okay. Here, our hardness is only going from about 30 to 60. So let's fix that. Format axes. We want to go from 30 to 60. And there is an extra zero here. We don't want all that. So we want to make the zero. Okay, we have three curves. Let's identify them. So let's put the legend at the top. So we don't want series 1, series 2, series 3. So let's give it some name. So we'll go to select data, series 1, edit, and this we know was room temperature toughness. Series 2, low temperature toughness. Series 3 is room temperature hardness. Okay, so we got all those. Let's add the usual chart title. And we have impact. Let's write hardness first. Actually, let's just write effect of tempering temperature. Okay, x-axis, tempering temperature. And again, notice this is in Fahrenheit. That's what the shop people use. That's where the furnaces are set in US. Let's add vertical. So that's our impact toughness. And that was in joules. And of course, we have a secondary axis, which is our Rockwell hardness. HRC. And folks, we are pretty much done. So let's move this plot to the right. Okay, one more plot. This time we want to study effect of carbon percent. So x-axis, we want room temperature toughness, low temperature toughness, average hardness. Insert. And again, let's move the chart. So this is our plot number 2. We are going to switch row column. And again, let's start by formatting the x-axis. So we'll plot between 0.15 and 0.5. That looks okay. Let's move hardness to secondary axis. Okay, so we see hardness is between something like 15. Let's see our data. So hardness is something between 0 and 30. So let's make it 0 and 30. It's already 0 and 30. Let's make it 15 and 30 then. And let's reduce number of digits to 0. Okay, so again we want legend. Let's give these names. So as before, series 1 is room temperature toughness. 2 is low temperature toughness. 3 is room temperature hardness. Okay, so we want to give chart title, effect of weight percent carbon. Okay, x-axis, weight percent carbon. Primary, impact toughness. Secondary, Rockwell hardness. And I guess we are good to go. Okay, folks, so we have two plots and our impact toughness. Okay, so let's see what our results mean. So let's see effect of tempering temperature. So this blue curve, red curve, impact toughness versus tempering temperature. And this gray curve is hardness. So first of all, we notice that as tempering temperature increases, our hardness goes down. However, notice our room temperature toughness as well as low temperature toughness both go up. Okay. Also, the low temperature toughness is always below the room temperature toughness. So there is some kind of a ductile to brittle transition going on. But our temperature was not low enough. If it was low enough, what would happen is we expect to see near zero impact toughness. So this red curve should have been essentially flat. Okay. What about the effect of weight percent carbon? So here weight percent carbon is increasing. First of all, we notice hardness increases. So as percentage carbon increases, hardness increases. So of course we expect toughness to go down. Okay, and we see, yes, the toughness goes down. Both the blue curve and the red curve are sloping downward. And of course, our room temperature toughness is higher than low temperature toughness. So again, in this plain carbon steel, there is ductile to brittle transition going on. And of course, our temperature was not low enough for doing low temperature toughness measurement. We would have expected again this red line to be effectively near zero values, but they are not. Okay, typically when we measure impact toughness, there is a lot of scatter. So as I said, we need to test many specimens to get a single reliable toughness value. So often we do 5 or more. In our case, we have 3 sets of data. So for your assignment, I'm going to take the first set we just did right now, give you 2 more sets of data, and you are going to do the average from all of these 3 sets, and then do the same plot like I did, plot 1 and plot 2. As you saw, there was very little data to process. I'm not going to list the discussion and conclusions, so you should have been taking notes while you were watching the video previous few minutes. And of course, if you have any other observations, you're welcome to email me and your TA to share your insights just from this demo discussion itself. Okay, folks, we are about at 1 hour mark or so in this video. A few of you have complained that the lab videos are long, could be condensed. It would help me to know what parts you would like me to condense. So in your surveys, you can identify from time so to time so in the video I could condense. I'll really appreciate that. But in any case, let's be reasonable. In in-person classes, you would have attended up to 2 hour class each of the 2 weeks for a given lab. So if we were to replace them, you would have had a 4 hour video. So be thankful. Okay, the second part of our lab, I hope you enjoyed very much. It has got hands-on activities. We are again going to focus on indentation hardness. But before I really go to indentation hardness, I want to share something with you. In my other course, numerical methods that I'm teaching, I am talking about all the accomplishments made by NASA in getting that rover onto Mars a few weeks ago. It's really a tremendous accomplishment. And here we are talking about distances of the order of millions and billions and trillions, right? On the other hand, let's look at the other extreme. In my course, we are looking at materials at atomic level, at microstructural level. So there is also a lot of room at the bottom. You might find that phrase elsewhere. Find out where that phrase is. The man who said it was a very famous man, and you could learn a lot from his books and writings. Anyway, indentation hardness. So we have been talking about hardness now in pretty much every lab, and I've been emphasizing that hardness is a function of yield strength. So that means, as everything else being equal, if you increase yield strength of material, its hardness increases. It's a function of elastic modulus. So that means if we increase elastic modulus, everything else being equal, we increase the material's hardness. And then there are two measures of strain hardening behavior, One called strain hardening exponent, N. You can look up your book. The other one, much more practical to me, is the strength ratio that we have been using. And as the strength ratio increases, again, hardness increases. Now, when we take a material and give it a mechanical treatment like plastic deformation, cold working, hot working, or we give it heat treatments like annealing, quench hardening, etc., we do not change elastic modulus at all because we are not changing the chemical composition. So in any thermomechanical treatments, we can only change yield strength and we can change strain hardening behavior. So far, when we have looked at indentation hardness equipment in lab 1, we looked at Brinell hardness test. In lab 2 and lab 3, we have looked at Rockwell hardness test, regular specimens, and superficial Rockwell hardness test for thin specimens. In this lab, we are going to look at micro indentation hardness test. We are going to focus on Vickers hardness this time. And then in the next lab, we will have a component on Knoop hardness. So we have been talking about different scales. Let's look at Brinell. So Brinell, we were using a 10 millimeter ball, making about a 5 millimeter diameter impression. We were using loads from 500 kgs to about 3,000 kgs. And this is typically used for cast iron, steel, non-ferrous alloys, typically for big pieces when we are trying to make large pieces. Then in Rockwell, there are many scales, A, B, C, D, E, F. We looked at B and C scales particularly. B scale is used for soft materials. C scale is used for hard materials. We also looked at the superficial corresponding T and N scale. We didn't do any experiment using N scale, but we looked at it. Today we are going to talk about Vickers, which is a diamond square pyramid indenter. And the loads we apply are of the order of something like 10 grams to about 2 kgs. And then, of course, as I said, we are going to do next lab Knoop indentation using an elongated pyramid. And again, loads are in the same range, 10 grams to about 2000 grams or so. Now, I particularly want you to understand when we looked at Brinell hardness number, in Brinell hardness number, we used a formula. We said it is force over the surface area of the indentation. So we had a formula. And this formula involved the diameter of the ball indenter, then the diameter of the indentation, which we measured manually or we measured using Fiji. We are going to skip Vickers hardness for a moment, Knoop hardness for a moment. Let's look at Rockwell hardness. So in Rockwell hardness number, whatever scale, it was proportional to some formula corresponding to minus h, where the machine measured this depth of indentation h and converted it into a number. And we had variety of scales. Today we are going to talk about Vickers hardness number, which is also force over surface area of the indentation. And there is a formula involved. Now, just to compare it next week, next lab, not next week, next lab, when we do Knoop hardness number. We are going to calculate it as force over area of indentation, not surface area, but area of indentation. Okay. And of course, we define Myers hardness number also as force over area of indentation. And we found out this Myers hardness number correlates very well with Rockwell hardness number and Brinell hardness number. Okay, so in this lab, we are going to compare Myers hardness to Vickers hardness. Even though we don't convert from one scale to another, but it might be worthwhile to look at this various hardness scales. So you can see this is Knoop hardness, this is Brinell hardness, spans a long range. This is B scale Rockwell, soft scale. This is C scale Rockwell. And this is Mohs hardness, which is usually used for minerals. Okay, so we have a micro hardness tester. It's a manual tester. Let's look at different parts of it. Hi folks, this is our micro hardness tester. It is made by Lico Corporation. It is model LM247AT. Let's go from the top. So this whole thing is our micro hardness tester, and then we have some accessories. We have a series of lenses connecting to a camera, which is connected to this computer. So once we make an indent, we can take an image and then do measurements if we want to. Now the machine itself is capable, without doing any image analysis, to do calculation of the hardness after manual measurements using this eyepiece. So we have a camera, which is an accessory, and then on the right hand side we have a dial where we can choose the load that we want to apply. So the smallest load we can apply is 10 grams, 10 G, and the largest load we can apply is 1000 gram, 1 kg. Typically we apply loads between 200 to 500 grams. Then we have an eyepiece. Built within the eyepiece are two glass bars which allow us to make distance measurements. So we have basically a dial which we can move the bars to and do a reading. We can also rotate this eyepiece through any angle. Typically we make two measurements in Vickers hardness at 0 degrees and at 90 degrees. Next we have this turret. The turret can accept 6 things. Right now we have only 4 of those 6 positions occupied. We have 2 indenters, one a Knoop indenter, other a Vickers indenter, and then we have 2 objectives, a 10x objective and a 50x objective. So coupled with this 10x eyepiece, we can magnify our indentation 100x or 500x. Then next we have our sample stage. So for let me take the sample out. So what we need in order to make a micro hardness measurement is a polished surface. It should have a mirror polish. So typically we take a piece of metal, we mount it in Bakelite, and then we polish it. We'll be doing this in our next lab. Now to mount this is our universal sample holder. So it has got this pivot here, which allows us, so even if these two surfaces were not parallel, it allows us to mount our sample such that the top surface is always horizontal, flat and horizontal. The next thing what we have here is we have a LED scope through which we can make measurements. It's a touch screen, and then here we have this dial which allows us to raise the sample up or down to focus it. Now on the sample stage we also have these micrometer assists so that we can move the sample in X direction or Y direction. Typically what we want to do is we want to make several hardness measurements, several indentations, so we might want to space them apart. In the video, it is not easy to see what a universal mount looks like, but it looks like this. It has got two knife edges, and I slide my sample, which is my mounted polished sample, with the surface up, put it against the two knife edges, and then I'm just going to take this and tighten it, raise it up to mount the specimen. So once the specimen is mounted, we are ready to do hardness testing. Okay, so we are going to make a Vickers hardness measurement. At the back, we have two power switches. One is the regular power switch, which we usually leave on. The other one we switch on when we want to use the machine. It lights up our LED, and the first thing we are going to do is prep up. So we want to do hardness Vicker. So it's a touch screen. We can select our hardness Vicker. We want a 10-second dwell time when we are going to apply this 500 kg load. So here is my dial. I've set it up at 500 kg, and I am ready to make measurements. So the first thing I want to do is I want to reset my glass cursors. So I have two glass cursors which I'm going to bring them very close without crashing into one another by rotating this filer unit. Once they are closed, I'm going to press this reset button, and that will tell the machine that this is zero distance. Then just to be on the safe side, I'm going to put the glass cursors apart. I have already mounted my specimen, and what I'm going to do is I'm going to bring my 50x objective and bring my sample into focus. Now what I can do is, if I have many features, I may first want to bring my 10x objective, look at a big picture, find where I want to make the hardness measurement, and then switch to my 50x objective to do a fine focus. Once I have done that, I am ready to make the measurement, and I press the start button. So when I press the start button, it brings the Vickers indenter on top of the specimen, lowers the indenter, makes the indent, is going to stay there for 10 seconds, applying that 500 gram load. And then once it has unloaded, it brings the 50x objective into position automatically. So now I'm going to improve the focus. The focus goes away a little slightly. My indent is slightly off center. And so now what I'm going to do is I'm going to bring the glass cursors to the two corners. And once I'm satisfied, I'm going to press read. So I've now made one diameter measurement. I'm going to rotate my filer unit and make the other diameter measurement. Press read, and it has now got two diameters. One is 72 microns, other is 71 microns. It does the calculation and says hardness Vickers is 178.1. So now if you want to make another hardness measurement, what we can do is, we have this reading. Right now it is at 0.25. I'm going to move it by another 0.05, and I'm ready to make my next hardness measurement. Thank you. Okay, so let's look at how this Vickers hardness number is calculated. So we have this square pyramid indenter. The angle it makes, the two faces, is 135 degrees. This is angle we'll call alpha. And this is what the indentation looks like under the microscope. So we make two diagonal measurements, D1 and D2, and then average it. So our Vickers hardness is defined as test force divided by surface area. So we applied 500 grams, that's half a kg. We will divide by surface area in millimeter square. Now, based on this geometry, we can calculate the surface area to be the average diagonal square over 2 sine alpha over 2. Since we know alpha is 135 degrees, this formula reduces to this particular simplified version. So we can calculate, once we know what the force is, and once we know the average diameter, we can use this formula to calculate our Vickers hardness. So please create another Excel sheet named hardness in the same workbook as your impact, based on this PDF that I have posted on my courses. You're going to use nearly identical uh, Excel worksheet for your assignment. So let's copy this formula down before I start typing in my Excel. So our surface area alpha was 135 degrees, and our surface area is diagonal square over 2 times sine alpha over 2. Okay, so let me fire up my spreadsheet. Here is my spreadsheet. Okay, named hardness. So I performed these tests a few days ago. This is our tester. We are going to use Fiji ASTM standard. We have a metallographically polished surface. For my sample, demo sample, I'm using a LICO calibration standard. For your assignment sample, I'll be giving you a 1018 steel. So for this standard, we know the Vickers hardness at 500 gram force, it's 531.02. And it is also used for NUP calibration, so I'm just listing it here as completeness. At 500x, when I took the images, the resolution of the image was 5 pixels per micron. So what we can do is we can calculate the resolution of our image. So 1 divided by 5. So our resolution is 0.2 microns per pixel. Our angle is 135 degrees. Let's give it a name, alpha. Our force is 0.5 kgs. Let's give it a name, force. And this is our standard hardness that we expect. So I made 6 indentations, as you saw in the video, not the same sample, I had a different sample. And these are my 6 measurements. Okay, let's look at how good they are. So you're going to take average of these 6 measurements. So the average comes out to 534. We expected 531, so that's 3 out of 500, less than a percent. Okay, let's look at standard deviation. $12.6, so this is between 546, 522. Pretty large scatter. I would have preferred it to be within plus minus 6, but 12 is okay. All right, so we are ready to make our indentation measurements. So here are our 6 indents. So I have loaded 6 images, TIFF images, on my courses, and let's fire up Fiji. So what I'm going to do is I'm going to open all images, V6 through V1, because I want first one to be 1. So let's start File, Open, and I'll start with 6. Go to 5, 4, 3, 2, and 1. And then I'm going to set my scale. So I'm going to go to Analyze, Set Scale. And my resolution of the image was 5.014 pixels, was 1 micron. And I'm going to make it global for all images. Measurements I want to do, I want area, perimeter. I want to add to the overlay, display label, scientific notation, 4 decimal places. So for each image, what I'm going to do, I'm going to draw a rectangle around the indent. Then I'm going to crop it. So I'm going to be careful that my indent does not touch my border. But I want to also not draw too large a rectangle. Then once I crop it, I'm going to change the image type to 8-bit, which is grayscale. And I'm going to apply a threshold to convert it to a binary image, black and white image. Okay. All right, here we go. So I have a rectangle. I'm going to draw a rectangle. So notice I'm not touching any of the indent borders. image, crop. Okay. Then I'm going to turn the image into 8-bit. And then I'm going to adjust the threshold. And usually it does a very good automatic job, nice automatic job. But if you want to adjust, you can adjust this bar. So I say apply, and I close. Second one, draw a rectangle. Image, crop, image, adjust 8-bit, threshold. Okay, next, same thing. Okay, I'm on to image 5. And finally, the last image. Okay, so we have processed all the images. Now we are going to measure the horizontal and vertical diagonals. So in order to really keep our spreadsheet clean, best would be to measure horizontal diagonals first and then vertical diagonals. So let's pick up BH1. We want to measure horizontal diagonal, Control M. Go to the next image, horizontal diagonal, Control M. Next image, Control M. Next image, Control M. Next image, Control M. And finally, last image, Control M. So the key idea here is we have got horizontal diagonals here, and we can just copy this column and paste it into our spreadsheet. Next, we are going to measure again 1 through 6, the vertical diagonals. So let's start with 1, and we do vertical diagonals. Control M. 2 vertical diagonals. 3 4 5 and last one 6. Okay, so we got 6 more diagonals here. Okay, so the next step what we are going to do is we are going to measure the area of indent. So this we are going to do by doing analyze particles. Okay, this is the window we are going to look at. What will happen is in some images there might be some stray particles. Some pixels are there somewhere, like there is this sliver hanging around. We don't want to measure it, so we want to exclude it. So obviously this is more than 10, this is less than 10 micron square or so. So here is what we are going to do. Go to first image, and then we are going to say analyze particles. And in this we are going to say we only want sizes from 10 to infinity. We want to display results, and we want to include the holes. So some might, you saw some might had holes. So let's say okay. So we find there was only one particle. This was the area, 867 micron square. So we are going to do the same for every one of those. 2, analyze particles. Okay. 3, analyze particles. 4, analyze particles. 5, and then finally last one, 6. And here we are. So we are going to save as, and let's give it some name, Lab4 demo record. So close this, file, close all. And of course you can save these images. I've saved them many times, so I don't want to save them anymore. Okay folks, so what we can do is we can import that data. So we can open that sheet. Let's see, it was called demo for record. Take all of this, copy, go into our other spreadsheet, and we can say paste. So this is from Fiji. Okay. So we saved the table, we transferred the values to Excel sheet. So now let's see what we are going to do for processing. So we are going to take the first 6 lengths, copy, and that's our diameter. So we want just values only. We don't want to mess up the um, formatting. Next 6 values, copy, paste. And then we want next 6 area values, copy, paste. Okay. So we want 2 digits, and 2 digits. Okay, so we can take the average of the 2 diagonals, and remember our formula, force divided by surface area, and surface area was diagonal square divided by 2 times sine of our alpha is in degrees, so we want to convert it into radians, and that should be it. Oh, millimeter squares. So our area is in micron squares, so let's multiply it by a million. Okay, what's our Myers hardness number? Force divided by area, and again area is in micron squares, so 1 million. Now let's also calculate this. Vickers hardness was calculated using Fiji. This Vickers hardness was from our manual measurements. So let's find our difference. So we'll take this value divided by measured minus 1 times 100. Okay, so let's adjust some digits here, just digits. And we'll copy all of these formulas down. Okay. We could have copied the formats too selectively, but this is just as fast. Okay. And let's copy average those formulas as well. Okay. Okay, we need one plot. So we are going to plot Vickers hardness versus Myers hardness. So insert plot. So first thing we do is we move the chart. So this is our plot number 3. Okay, and let's start formatting it. So let's start with this, and let's format axes. Too many digits there. Same thing here. Okay, and let's start giving a chart title. So Meyer versus Vickers hardness. Axis titles, Vickers hardness, kgf, millimeter square. Okay, vertical, Meyer hardness, kgf per millimeter square. Okay, let's see how good the trend is. We expect really a perfect straight line ideally, but let's add a trend line, linear. We do want equation r square, and oops, let's move it here. So it's a pretty nice equation, about 0.88, slope of nearly 1. Okay, let's also go, let's move this over. Do we need anything else? No, that's pretty good. All right, so since it is difficult to import from graphical object, just like we did in the last lab, we are going to calculate intercept. So y values, comma x values. Okay. Slope, y, comma x values. And r square, y, comma x values. Okay, so let's go ahead. File, save as, and I want macro enabled book, and let's just say lab record. Okay. Okay, so let us discuss our results. So first of all, the spreadsheet that I'm showing you is different. It is not at the time when I made the recording. It's a spreadsheet that I made prior to it. So these are my measurements. They are the same. So you'll see the same average and same standard deviation. And so my measurements are pretty good. My first measurement seems to be uh, quite a bit off. Rest are pretty decent. Here are my diameter measurements from my Fiji. Remember, again, this is not from the video recording, so my numbers are different. Area, and then I have done these calculations. So what does my plot looks like? So my plot looks something like this. Actually, it is poorer than the one I made in video recording. It has an R square of only 0.73 because I have this one point which is way outlier. So I can kind of play around with it. I can exclude this point. So I can go to select data, edit, and I can say ignore the first point. So I can start from row 21. And notice what a big difference it makes. Now I have a R square of 0.95, and this is a pretty good straight line with a slope around. I would have ideally wanted 1, but it is like 1.66. So we have really a very good match. Fiji does a very good analysis. In fact, by playing with threshold and by carefully doing measurements, we can get a very, very good match. Okay, again, this demo specimen was a calibration standards, and you saw that the indents were nearly perfect shapes. When I give you the assignment specimen, that is a real specimen, 1018, and your indents are not going to be that perfectly shaped. Uh, Again, as I said, please listen to my discussion, take your own notes, uh, and if you have any other observations, please email me and your TA, and I'll be happy to discuss it with you. Thank you.